All right. Good morning, and my name is Kan-Heng, and I'm a research scientist in the Content Information Science and Technology group at Berkeley Lab, and I'm also currently the fabrication lead at our program, Advanced Content Testbed, which is what I would like to introduce you today. So we are already halfway through the content days at NERSEC, and I hope people already get the message that Berkeley Lab has really been dedicated ourselves into building the content technology for the futures. And we have, I think, up to like 7 different programs that's going on at Berkeley Lab, working on different parts of quantum computing, from superconducting qubits to trap ion, and from fundamental material science all the way out to quantum applications like the one we are doing at NERSEC. And for Advanced Quantum Testbed, we are really focusing on building up an advanced superconducting quantum computing platform and use that as a basis to form research collaboration with people all over the world in order to kind of progress the quantum technologies. And the reason we are doing this is really based on 2 core philosophy. And the first one that I think most of the people in our field will agree is that building quantum computer right now is not just a pure engineering problem. There are actually still a lot of fundamental scientific questions that we need to understand in every part of building a quantum computer. And there are even more fundamental questions inside this overlap between the parts. However, this is also very challenging in the sense that this problem of building a full stack quantum computer is way too complicated for an average academia group because of the technologies and the infrastructure that you need to build a full stack quantum computer, but it's also too expensive with unknown return of investment for a lot of business to do it. And this is where we want AQT to sit at. We want to be a place where we have all the technologies that you need to build a full stack quantum computer, but we want to do fundamental research. But this research, we want it to be relevant to building full stack quantum computer. And the second core idea that AQT have is we want to keep explore the possibility for quantum computing. So you can look at the whole quantum computing field, and you see all kinds of different platforms: superconducting qubit, trap ion, neutral atom. And if you are a positive thinker, you will think that there are so many candidates, promising candidates, and will definitely one day get a quantum computer. But if you are a negative thinker like me, I think we are doing everything because we don't know what to do. So I think the most important thing is to keep explore the possibility. And I think to do that, we really need to broaden our collaboration with all the scientists around the world who have different ideas here. However, if you want to really try different things and remain flexibility, then you really need to be able to do every part of the quantum computing. For example, if you have a quantum application that will require you to change the hardware of your quantum processor, then we want to be able to do that. So we call this a hardware-aware quantum application. That means we want to be able to build a full-stack quantum computer, but eventually we want to focus on the application of the computer. So with that, this is the kind of what we are doing in the AQT space. So we are building full stack. So we work from everything from cryogenic equipment to design and fabricate superconducting quantum processor, all the way down to making control hardware and developing the software stack. And here is a top view of our lab space, which is rather small considering how many things that we are working on. But in the past year, we have been working on moving into a newer, bigger space like the one here. We are really looking forward to move into here. And this is to host our growing team, because now we are facing more and more difficult challenges as the quantum technology evolves. So in the next 10 minutes, I want to show you some results from AQT on all parts of quantum computing. And let's start with the superconducting quantum processors. So at AQT, we have our own superconducting qubit fabrication clean room. So we are able to get a very fast turnaround time on making the device. So we have been trying all kinds of different ideas on QPU architecture. And here are just some examples that we have tried over the years. And among them, there are two that really my favorite. And the first one is a SpiderNet QPU. Now, if you ever meet a tri-ion person like Erhan, you ask what is so special about tri-ion than superconducting qubits, one of the biggest points they will make is probably like tri-ion can have all-to-all connectivity, right? And now you can try error correction beyond just surface code. Now, if you look at all the superconducting qubit processor, they always have connection to only the nearest neighbor. Then the question is that limited by fundamental physics? So here we prove it's not. So we build this SpiderNet QPU where all 8 qubits on the chip are connected together through one bus coupler. And then by tuning this bus coupler, we can pair any 2 qubits together to do 2 qubit gates. So basically you can have all-to-all connection for superconducting qubits too, if you ever want to try an error correction beyond surface code. Another one that this is the work that I work with a graduate student here, is the Everglade architecture. So one big problem for superconducting qubit is that it's built with solid state materials, and you always have defects in materials. Even worse is that the defects in these materials that affect the qubit is kind of random. They fluctuate in time, they fluctuate in frequency. You don't know when they will come in and kill your qubits. So that's a big problem. And what people are doing today, I think the most effective way is to use AI plus machine learning and try to tune the qubit away from the defect when the defects start affecting your qubits. But it's clear, like, one, for small company, that will be very hard to do. You don't have the resource. And two, when we scale up to millions of qubits, the time that the classical computer will need to recalibrate the system will probably be more than the time that your defect fluctuate. And then every time you recalibrate, your qubit is dead again. So what we are trying to solve here is we try to rethink the qubit architecture and think about whether we can actually tune the TLS instead of the qubit at the hardware level. So we designed this Everglade architecture where we can just apply a voltage, and here the red curve is where the defect is affecting the qubit, and you can see that we can move it away in the frequency. And by doing so, we can improve the gate infidelity of our processor by 36% without recalibrate the qubit for, I think, 48 hours is what we are doing here. So I think this is a very interesting thing that we have been trying here. And finally, like I say, there are many programs in Berkeley lab, and usually when you have some problems, you can walk into a different program and find the solution there. So what we have here is for superconducting qubits, we usually have to do electromagnetic wave simulation, but it's very resource hungry simulation. So we usually can only do 1 to 2 qubits. So we work with QSA, Andy, and Jackie's group and their team to build up this new capability where we can not only simulate medium scale, in this case 14 qubit chip, but also get time domain information. So in this case, we actually work with NeurSec2, use the supercomputer with more than 6,000 GPU, and then we simulate the whole 14 qubit chip. This was a time-lapse movie, but I only have a screenshot here. But we can actually get the full time information of how it looks like when we send in a microwave pulse onto the chip. And I think we'll present these results in the next NVIDIA meeting very soon. Okay, and on the control front, AQT also have been, yeah. Hi.
What do you use the time information for? I know typically people do simulation in the frequency space when they design chips.
Yes.
Can you use the time domain for some design purposes, or what's the purpose of doing the time?
Okay, so in the frequency domain, everything is kind of steady state. But when we are operating the qubit, we are operating at a time scale of 10 to 100 nanoseconds. So a lot of pulse like interaction is transient. So there are a lot of like crosstalk that we are looking at through frequency domain simulation that we never see. So now we are looking at time domain information where like a ring out, ring down is actually not a fixed frequency, right? It's a distribution of frequency. So whether the crosstalk is coming from that or not, I think the time domain information will allow us to understand more of how these qubits work.
Would you be able to simulate something like TLS as a time domain as well with this technique?
TLS?
Yeah.
We haven't tried, maybe. You can probably simulate that as a qubit too. All right. So yeah, in the control, we also have a natively developed control hardware that is the qubit board. And because our control team developed everything on this from firmware to hardware, so we really have access to all aspects of the control at AQT. So this qubit board, the newest one, is built on the Xilinx ZU 216 FPGA board. Currently, we are mostly using this qubit board to control all of the QPU that we have at AQT up to 20 qubit systems in our fridge. And then because we have full access to the software stack, so we are able to really try a lot of things. And by the way, this is really impossible to do with commercial solution. That would never show you like the code base that they have, which we have tried for years. And by having the full access to software stack, now we can demonstrate a lot of new technology or like new techniques. Like here, one of our postdoc, Neely, was demonstrating a preliminary demonstration of mid-circuit measurement and feed-forward. So in this case, he actually did a conditional bit flip where you have a qubit 0 and we do a measurement. And after this measurement, if it's 0, then we do nothing to qubit 1. But if the measurement shows 1, then we do a bit flip on qubit 1. So this is the conditional bit flip. And we show that, and the results here show that indeed, we can successfully do this condition bit flip with a qubit board. And this will be useful in the future for mid-circuit measurement and error mitigation. Another thing that we can do here with the access to the full software stack is that we realize the compilation and a lot of the time that we spend on executing process like random compiling, the time are actually 90% spent on compilation and transpilation. That means the time we wasted on waiting, the circuit is actually wasted on preparation of the execution rather than the circuit itself. So here, the control team was able to change the way the board compile and transpile the circuit. And here they show a threefold speed up in terms of the execution time for the same process by just changing the compiling and transpiling method. Okay, finally, for the quantum application at AQT, over a year, we have demonstrated a lot of interesting things and developed a lot of new capability in QCVB, quantum control, and quantum simulations. And yet, as you can see here, we have quite many publications. So I'll just pick two of, I think, representative work. And the first one is done by Akko, who will give a talk tomorrow on related topic. But here, the question that we are really asking is, for today's quantum computer, people always use randomized benchmarking to show you how good their quantum computer is. But the question is that accurate? Or how do we read this randomized benchmarking results and compare them between quantum computers? And here we show that randomized benchmarking is good, but if and only if you also do random compiling of your test circuit, That means depending on what circuit you use to run randomized benchmarking, you might have different noise on different quantum computer. So really you have to look at how they perform the randomized benchmarking in order to judge how good a quantum computer is. And if you are interested in this topic or how to verify a quantum computer, I think Akko will talk about this in tomorrow's afternoon's talk. And for a lot of people, when you get access to quantum computer, probably the most exciting thing to do is quantum simulation, because that's the whole idea. So we really want to try that at AQT too. And this is like one of my favorite simulations so far. This is about like simulating the neutrino. And so for neutrino, it is really interesting because for classical computer, it's quite hard to simulate. And also because the neutrino interaction is quantum in nature. So it makes it more complicated for classical quantum computer. Classical computer, but quantum computer make a lot of sense. But in this case, they also compare different quantum computer. So if you think about it, neutrino have 3 different flavors. So they have 3 different states. Now, if you want to simulate it with the qubit system, a qubit only have 0 and 1. So if you want to represent 3 states, now you need to tap into 2 qubit states. But in that case, you have 4 states, but you only need 3. So it becomes really inefficient. But at AQT, we actually been developing this Q-tree processor over the years. And in the Q-tree case, we actually use 0, 1, and 2. So there are exactly 3 states that map to the neutrino states. And the encoding of this simulation become very straightforward in this case. So we are able to demonstrate that indeed at AQT, we can use this Q-tree processor to simulate neutrino interaction with a very good accuracy when you compare it to classical computer. Of course, there's no quantum advantage here, but we just show that we can do this, and Q-tree processor is much more efficient than qubit processor in this case. And this also shows that there are a lot of future application of quantum computer beyond just qubit operation. So I would say that over the year, this user program has provided us very good, impactful results, and it was quite successful in terms of publication too. And now we have around 17 different collaborations with scientists all over the world. And for the next stage of AQT, we really want to take our experience in this academia collaboration and our capabilities to build full stack quantum computer into industrial collaboration. So in the past few years, we have been trying to form industrial partnership with all this company here. Some partnership already started, some are under process. But we hope that by bringing our experience in full stack quantum computing, we are able to kind of help and collaborate with the industry to shape what quantum technology will look like in the future. And that brings me to my last slide for AQT 2.0, which is our current phase. We really want to advance our full stack quantum computer technology to a multi-layer large QPU and the goal is to perform early error correction and more quantum application at a higher level. And we are hoping that by doing so with our collaborator, AQT can be a hub or a basis for the collaboration between academia, national lab, and industry to progress the quantum technologies for the future generation. And with that, thank you for your attention. And